What if the most promising places to find life beyond Earth aren't orbiting distant stars in far-flung solar systems, but right here in our own cosmic neighborhood? What if entire oceans exist hidden beneath frozen shells, harboring secrets we're only beginning to glimpse? For most of human history, when we looked up at the night sky and wondered about life beyond our world, we imagined it would be found on other planets. Mars, with its dusty red deserts, perhaps Venus, beneath its thick clouds. We assumed that if life existed elsewhere, it would need what life on Earth needs: sunlight, a rocky surface, an atmosphere. But the universe, as we've discovered again and again, is far stranger and more creative than our imaginations. Out there, orbiting the giant planets of our outer solar system, are worlds that have rewritten our understanding of where life might exist. Not planets, but moons. Not warm, sun-drenched surfaces, but frozen shells concealing vast oceans in perpetual darkness. These are the ocean worlds, and two of them stand out as the most tantalizing targets in our search for life beyond Earth. Their names are Europa and Titan. One orbits Jupiter, locked in a gravitational dance that keeps its hidden ocean liquid despite being 5 times farther from the Sun than Earth. The other circles Saturn, shrouded in an orange haze, with not one but 2 oceans, one of liquid methane and ethane on its surface, and another of water deep beneath its icy crust. Together, these 2 moons represent our best chance of answering one of humanity's most profound questions. Are we alone? Tonight, we're going to explore these alien ocean worlds. We'll trace the evidence that revealed their hidden seas, understand the energy sources that could sustain life in eternal darkness, celebrate the spacecraft that discovered their secrets, and contemplate what it means for our place in the universe. This is a story of detective work and discovery, of patience and wonder, of expanding our definitions of what's possible. So, settle in. Let the rhythm of this journey carry you gently forward, and let's begin our exploration of the oceans beneath the ice. To understand why Europa and Titan have captured the imagination of scientists and dreamers alike, we need to know what makes these moons so special. They're not just balls of ice and rock, indistinguishable from the hundreds of other moons in our solar system. Each has characteristics that set it apart, features that hint at the dynamic, possibly living worlds beneath their surfaces. Europa is small by planetary standards. At just over 3,100 kilometers across, it's slightly smaller than Earth's moon. It's the 4th largest of Jupiter's many moons and the smallest of the 4 Galilean satellites discovered by Galileo Galilei in 1610, along with its 3 larger siblings, Io, Ganymede, and Callisto. For centuries, Europa was just a point of light through telescopes, one bright dot among several orbiting the giant planet. But when spacecraft finally reached Jupiter and turned their cameras toward Europa, they revealed something extraordinary. The surface is smooth, remarkably, almost impossibly smooth. While most moons and planets are cratered and ancient, their face is scarred by billions of years of cosmic bombardment. Europa's surface is young. There are very few impact craters, suggesting that something has erased or covered the ancient impacts. The surface we see today may be only 40 to 90 million years old, a blink of an eye in geological time. That surface is crisscrossed with cracks, fractures, and strange features called chaos terrain. Long, dark streaks cut across the ice like the veins of a leaf. Some regions look like the surface has been broken apart and refrozen. The ice plates shifted and jumbled like a puzzle put back together incorrectly. The whole moon has a peculiar beauty, its surface colored in subtle shades of white, cream, and reddish-brown, as if someone took a pristine snowball and painted delicate lines across it with a fine brush. Europa orbits deep within Jupiter's powerful magnetosphere, bathed in intense radiation that would be lethal to any spacecraft, spending too much time nearby, and certainly lethal to any unprotected astronaut. This radiation environment posed enormous challenges for mission designers, but it also plays a role in Europa's story, as we'll discover. When Voyager 1 and 2 flew past Jupiter in 1979, they provided our first close looks at Europa. The images were intriguing, but limited. Scientists could see the smooth, striated surface and began to speculate about what could create such features. Some suggested that beneath the ice might lie an ocean of liquid water. It seemed almost too good to be true. An ocean on a moon of Jupiter, but the speculation persisted, and when NASA's Galileo spacecraft arrived at Jupiter in 1995 for an extended mission, Europa was a primary target. What Galileo discovered changed everything. The spacecraft measured Europa's magnetic field and found something remarkable. The field changed in a predictable way as Europa orbited through Jupiter's powerful magnetosphere. This wasn't Europa's own magnetic field generated by an iron core like Earth's. Instead, it was an induced magnetic field, created by a conductive layer inside the Moon, interacting with Jupiter's magnetic environment. The most plausible explanation for that conductive layer, a global ocean of salty water, somewhere between 80 and 170 kilometers deep, lying beneath an icy shell estimated to be 15 to 25 kilometers thick. And that ocean might contain twice as much water as all of Earth's oceans combined. Let that sink in for a moment. This small moon, smaller than our own, might harbor more liquid water than our entire planet. Not frozen in ice caps or locked in rocks, but liquid, moving, possibly warm in places. An ocean that has been there for billions of years, protected from space by its frozen roof, heated from below by forces we're only beginning to understand. If Europa is the mysterious ice princess, Titan is the orange giant, wrapped in secrets. Titan is huge. At 5,150 kilometers in diameter, it's larger than the planet Mercury. It's Saturn's largest moon and the second largest moon in the entire solar system, beaten only by Jupiter's Ganymede by a mere 2%. But size alone doesn't make Titan special. What makes Titan unique is its atmosphere. Titan is the only moon in our solar system with a substantial atmosphere. Not a thin wisp of gases barely clinging to the surface, but a dense, thick atmosphere richer than Earth's. The atmospheric pressure at Titan's surface is about 1.5 times Earth's surface pressure. It's so thick, so hazy, that for centuries we couldn't see the surface at all. Titan appeared in telescopes as a featureless orange ball, shrouded in mystery. That atmosphere is primarily nitrogen, just like Earth's, with a few percent methane and trace amounts of other organic compounds. Those other compounds are important. High in Titan's atmosphere, methane molecules are broken apart by sunlight and cosmic radiation, and the fragments recombine into more complex organic molecules. These molecules form a thick, smoggy haze that gives Titan its distinctive orange color. Some of these organic molecules, called tholins, rain down onto the surface like a slow, constant snowfall of complex carbon-based chemicals. For years, scientists wondered what lay beneath that haze. Was the surface solid, liquid, rocky, icy? The mystery persisted until the Cassini-Huygens mission arrived at Saturn in 2004, carrying with it a probe designed to plunge through Titan's atmosphere and land on whatever surface waited below. When the Huygens probe descended through Titan's atmosphere on the 14th of January, 2005, it revealed a world that was both alien and hauntingly familiar. The surface was solid, made primarily of water ice so cold that it's as hard as rock. But carved into that ice were river channels. There were rounded pebbles, smoothed by the flow of liquid. There were coastlines and what appeared to be dried lake beds. As Cassini continued its mission, orbiting Saturn and making repeated flybys of Titan, the full picture emerged. Near Titan's poles are lakes and seas. Not water, of course. It's far too cold for liquid water on Titan's surface. The average temperature is a brutal 94 Kelvin, which translates to about minus 179 degrees Celsius or minus 290 degrees Fahrenheit. At those temperatures, water is as hard as granite, but methane and ethane remain liquid. And Titan has lakes and seas filled with liquid hydrocarbons. Kraken Mare, the largest, is bigger than the Caspian Sea on Earth. Ligeia Mare and Punga Mare are smaller but still substantial bodies of liquid methane and ethane, with coastlines and bays and inlets. Titan has a weather system with clouds and rain, except the rain is liquid methane. It has a hydrological cycle, just like Earth, except the liquid is hydrocarbons instead of water. This makes Titan the only other world in our solar system with stable bodies of liquid on its surface. The only other world where rain falls from clouds, flows down channels carved into the landscape, pools into lakes and seas, and evaporates back into the atmosphere to begin the cycle again. But the surprises didn't stop with the surface discoveries. As Cassini continued to study Titan, measuring its gravity field and observing how it responded to Saturn's tidal forces, evidence began to mount for something even more remarkable. Beneath the frozen water ice crust, beneath the organic-rich surface, Titan appeared to have another ocean. This one was liquid water, likely mixed with ammonia to keep it from freezing, sitting perhaps 55 to 80 kilometers beneath the surface. Titan, it turns out, is a double ocean world. Hydrocarbons above, two entirely different liquid environments, each with its own potential for chemistry, for energy flow, for the kind of complexity that, on Earth at least, led to life. Both Europa and Titan orbit giant planets. Both are subjected to tidal forces from their massive hosts. Both have icy surfaces concealing liquid oceans beneath, but they're profoundly different in almost every other way. Europa is small, cold, and radiation-scoured, with a young, active surface suggesting connection between the ice above and the ocean below. Titan is large, hazy, and organic-rich. Yet despite their differences, both moons represent the same tantalizing possibility that life might exist in places we never thought to look. Not basking under the warmth of a nearby star, but thriving in darkness, powered by forces other than sunlight, in oceans that have been stable for billions of years. And the evidence for those oceans, accumulated painstakingly over decades of observation and analysis, tells a story of scientific detective work at its finest. How do you prove that an ocean exists when you can't see it directly? When it's hidden beneath kilometers of ice on a world hundreds of millions of kilometers away, you look for clues. You measure, calculate, observe, and piece together evidence from multiple sources until a picture emerges that's too compelling to ignore. The evidence for subsurface oceans on Europa and Titan is one of the great detective stories of planetary science. It's a tale told in magnetic field measurements, surface features, gravitational anomalies, and spacecraft data analyzed and reanalyzed for decades. Let's trace how we know what we know. The story of Europa's ocean begins with magnetism. When NASA's Galileo spacecraft arrived at Jupiter in December 1995, one of its instruments was a magnetometer designed to measure magnetic fields. As Galileo made its 11 targeted flybys of Europa over the course of its mission, the magnetometer detected something peculiar. Europa has no magnetic field of its own, at least not one generated by a molten iron core like Earth's. But as Europa orbits through Jupiter's powerful magnetic field, which is about 20,000 times stronger than Earth's, something inside Europa responds. The magnetometer detected an induced magnetic field, one that changed in strength and direction as Europa moved through different parts of Jupiter's magnetosphere. This was the first major clue. An induced magnetic field requires a layer of electrically conductive material inside the moon, and the best candidate for that conductive layer, given everything we know about Europa's composition and structure, is a global ocean of salty water. Salt water conducts electricity well. Pure ice doesn't. If Europa had a subsurface ocean with dissolved salts, it would interact with Jupiter's magnetic field in exactly the way Galileo observed. The magnetic field data suggested the conductive layer was relatively close to the surface, probably no more than 30 kilometers down. This fit perfectly with models suggesting an ice shell 15 to 25 kilometers thick, overlying a deep ocean. But magnetic field measurements alone, compelling as they were, weren't the only evidence. Scientists also looked carefully at Europa's surface, and what they saw there told a consistent story. Remember those cracks and chaos terrain we mentioned earlier? Those features suggest that the icy crust can move and shift, that it's not rigidly attached to whatever lies beneath. Some of the fractures on Europa appear to be tidal cracks, formed as Jupiter's gravity flexes the moon during its slightly elliptical orbit. The pattern of these cracks shows that Europa's outer shell can rotate independently of its interior, which makes sense if there's a liquid layer between the crust and the rocky mantle below. The chaos terrain is even more suggestive. These regions look like the surface ice has been broken apart, with blocks of ice tilted, rotated, and refrozen in new positions. Some areas show what appear to be upwellings of material from below, as if warm, less dense ice, or even liquid water pushed up through the frozen crust, melted the surface ice, and then refroze. If Europa's ocean occasionally breaks through to the surface, it could explain both the young age of the surface and these chaotic features. Then there's the tidal flexing itself. Europa orbits Jupiter in a slightly elliptical path, drawn into that ellipse by gravitational resonances with two other Galilean moons, Io and Ganymede. As Europa swings closer to Jupiter and then farther away with each orbit, Jupiter's gravity pulls more strongly and then less strongly on the moon. This causes Europa to flex, to deform slightly, bulging toward and away from Jupiter in a rhythm that repeats every 3.5 Earth days. Scientists measured how much Europa flexes by observing small changes in its shape and gravitational field. The measurements showed that Europa's surface rises and falls by about 30 meters during each orbit. Now, if Europa were solid ice all the way through, or if the ice shell were frozen solid to a rocky interior, it would only flex by about 1 meter under Jupiter's tidal forces. The fact that it flexes 30 times more than that is powerful evidence for a liquid layer beneath the ice that allows the outer shell to move more freely. But perhaps the most exciting evidence came from observations of water vapor plumes. In 2012, using the Hubble Space Telescope, scientists observed what appeared to be plumes of water vapor erupting from Europa's south polar region. The observations were at the limit of what Hubble could detect, and subsequent observations in 2014 and 2016 found hints of similar plumes but weren't definitive. The big breakthrough came in 2018 when scientists took a fresh look at old data from Galileo. During one particular flyby of Europa in 1997, called the E12 flyby, Galileo passed within just 206 kilometers of Europa's surface. At the time, scientists noticed some odd readings in the magnetic field and plasma wave data during a brief 3-minute window. The magnetic field suddenly changed strength by about 200 nanoteslas and the plasma density spiked. Those anomalies went unexplained for over 20 years. But when researchers used computer simulations to model what would happen if Galileo flew through a water vapor plume, the simulations reproduced the observed data almost perfectly. Galileo, it appears, flew through an active water plume erupting from Europa's surface without anyone realizing it at the time. These plumes, if they're real and recurring, are incredibly important. They mean that material from Europa's subsurface ocean is being ejected into space, where a spacecraft could sample it without having to drill through kilometers of ice. They provide a direct pathway for ocean material to reach the surface and beyond. Scientists have also detected salts and minerals on Europa's surface, particularly in the reddish-brown material that colors some of the younger features. Spectroscopic analysis suggests these could be magnesium, sulfate, and other salts. Precisely what you'd expect if ocean water was reaching the surface, depositing its dissolved minerals as it evaporates or refreezes. Taken together, the evidence is compelling. Magnetic field measurements indicating a conductive layer, surface features suggesting a mobile ice shell decoupled from the interior, tidal flexing far greater than a solid body would experience. Possible water plumes carrying ocean material into space, salt deposits where ocean water may have reached the surface. Each piece of evidence points to the same conclusion. Beneath Europa's fractured ice shell lies a global ocean of salty water, perhaps 100 kilometers deep, that has existed for billions of years. The evidence for Titan's subsurface ocean is different from Europa's, in part because Titan's thick atmosphere obscured its surface until relatively recently, and in part because the ocean is much deeper beneath the surface. The first major clue came from Cassini's radar observations. Cassini carried a radar instrument that could penetrate Titan's hazy atmosphere and map the surface below. Over several years and multiple flybys, Cassini built up a detailed map of Titan's surface features. Mountains, lakes, dunes, and various geological landmarks. But when scientists compared the positions of these features in images taken years apart, they noticed something strange. The features had shifted, not by a little bit, but by as much as 30 kilometers from where they should have been if Titan were rotating at a constant rate, locked to its orbit around Saturn. This was puzzling. Titan is tidally locked to Saturn, meaning the same face of Titan always points towards Saturn, just like the moon always shows the same face to Earth. A tidally locked moon should rotate at a very predictable rate. But Titan's surface features were moving. The only explanation that made sense was that Titan's icy outer shell was sliding independently over the moon's interior, decoupled from the rocky core below. And the only way that could happen is if there's a liquid layer between the crust and the core. That liquid layer acts like a lubricant, allowing the outer shell to slip and shift over the interior. Further evidence came from measurements of Titan's spin rate. Using Cassini's radar data collected over several years, scientists determined that Titan's rotation is not perfectly synchronous with its orbit. Instead, it oscillates slightly, spinning a bit faster and then a bit slower in a pattern that repeats with Titan's seasons. This variation in spin rate can be explained by the interaction between Titan's dense atmosphere and its surface. As winds blow across Titan during different seasons, they exert drag on the surface, speeding up or slowing down the rotation of the outer shell. But this only works if the outer shell can rotate independently of the interior, which again requires a liquid layer beneath the crust. Scientists also measured Titan's tides. Just as Jupiter raises tides on Europa, Saturn raises tides on Titan. By precisely measuring Titan's shape as it orbits Saturn, scientists determined that Titan deforms significantly in response to Saturn's gravity, much more than a solid body would. The measurements showed a tidal deformation that could only be explained if Titan has a liquid interior layer beneath its icy shell. When scientists measured Titan's gravity field, they found additional evidence. The gravity data, combined with measurements of Titan's moment of inertia, how mass is distributed inside the moon, suggested an internal structure with distinct layers. A rocky core, a high-pressure ice layer, a liquid water ammonia ocean, and then the outer ice crust we see. Even the Huygens probe's descent in 2005 provided evidence. During its descent, Huygens measured radio signals that, when analyzed carefully, suggested the presence of a conductive layer 35 to 50 miles beneath the surface. This matches beautifully with the ocean depth estimates from other methods. The picture that emerges is of an ocean sitting 55 to 80 kilometers beneath Titan's surface. This ocean is likely a mix of water and ammonia, which acts as antifreeze, keeping the water liquid even at temperatures well below water's normal freezing point. The ocean is salty, denser than pure water, which helps explain some of the gravity measurements, and it's likely quite deep, perhaps 100 kilometers or more. The ice shell above the ocean varies in thickness. On average, it might be 20 to 25 kilometers thick, but near the South Polar region, it appears to thin to just 1 to 5 kilometers. This thinning could allow heat to reach the surface more easily in those regions, and might explain why some of Titan's surface features appear to be relatively young. Both Europa and Titan have given up their secrets gradually, through careful observation and clever interpretation of subtle clues. The evidence has accumulated over decades, each new measurement adding to our confidence that these hidden oceans are real. But knowing that the oceans exist raises an even more profound question. If you were to stand on the surface of Europa or dive beneath Titan's haze to its frozen crust, you'd experience cold beyond anything on Earth. Europa's surface temperature hovers around 110 Kelvin at the equator and drops to just 50 Kelvin at the poles. In Celsius, that's about minus 160 to minus 220 degrees. Titan's surface is a relatively balmy minus 179 degrees Celsius. These are worlds of eternal cold, so far from the sun that sunlight provides only a tiny fraction of the warmth it gives Earth. Yet beneath the frozen surfaces, the oceans are liquid. Water that should be frozen solid remains in motion. This seems impossible. Yet it's not only possible, it's happening. The key is understanding where the energy comes from. Imagine you have a rubber ball. If you squeeze it and release it once, it returns to its original shape with no problem. But if you squeeze and release it repeatedly, rapidly, the ball begins to warm up. That warming comes from the friction of the rubber molecules moving against each other as the ball deforms and returns to shape. This is essentially what happens to Europa and, to a lesser extent, Titan. Europa orbits Jupiter every 3.5 Earth days. If that orbit were perfectly circular, Europa would experience a constant gravitational pull from Jupiter, and there would be no tidal heating. The Moon would maintain a constant shape, bulging slightly toward Jupiter in a static tidal bulge, and no internal friction would be generated. It's elliptical, meaning Europa swings closer to Jupiter and then farther away with each orbit. Why is the orbit elliptical? Because of a beautiful gravitational resonance with two other Galilean moons. For every one orbit Europa makes around Jupiter, Io makes exactly 2 orbits, and Ganymede makes exactly half an orbit. This precise 4:2:1 resonance means the moons regularly align in ways that tug on each other's orbits, maintaining Europa's orbital eccentricity despite tidal forces from Jupiter that would otherwise circularize the orbit over time. Think of it as a cosmic conspiracy. Jupiter's gravity wants to pull Europa into a circular orbit, but Io and Ganymede keep yanking Europa's orbit back into an ellipse. This tension between circularization and perturbation has been maintained for billions of years, creating a perpetual source of internal heating. As Europa swings through its elliptical path, Jupiter's gravity pulls more strongly when Europa is closer and less strongly when it's farther away. This changing gravitational force literally squeezes and stretches Europa, raising tidal bulges on the Moon. The bulges aren't just in any liquid oceans, but in the solid body of the Moon itself. Europa flexes. The extent of this flexing is remarkable. Scientists estimate that Europa's surface rises and falls by about 30 meters during each orbit. Imagine standing on Europa and watching the ground beneath you rise and fall by the height of a 10-story building every few days. Of course, the changes happen too slowly to see directly. When Europa flexes, the internal friction generates heat. Rock grinds against rock deep in the moon's interior. Ice crystals shift and slide within the ice shell. The friction from these movements converts orbital energy into thermal energy. This process is incredibly inefficient in human terms. Most of the orbital energy remains as orbital energy, but over billions of years, even a small amount of heating is significant. Scientists estimate that tidal heating generates perhaps 100 trillion watts of power within Europa. To put that in perspective, that's about 200 times the power output of all of Earth's power plants combined. Yet, Europa is much smaller than Earth, so this energy is concentrated in a smaller volume, making it even more significant relative to the moon's size. This heat has profound consequences. It keeps Europa's ocean liquid despite the moon being far from the sun. It drives geological activity that resurfaces the ice shell, erasing ancient craters and creating the chaos terrain we see. It may power convection in the ocean, circulating water and distributing heat. Titan experiences tidal heating too, though the effect is weaker because Titan's orbit around Saturn is less eccentric than Europa's orbit around Jupiter. Titan's orbital eccentricity is only about 0.03 compared to Europa's 0.01, meaning Titan's distance from Saturn varies less dramatically. Still, the tidal flexing generates some heat, and recent models suggest this heat might be more significant than previously thought, particularly if Titan has a porous, rocky core. The key insight about a porous core is that it changes how tidal heating works. In a solid, non-porous core, the tidal flexing directly heats the rock through friction. But in a porous core, the tidal flexing also moves liquid water through the pores, creating friction between the moving water and the rock. Think of it like water flowing through a sponge. The friction between the water and the sponge material generates heat. In Titan's case, if the rocky core is porous and water from the ocean can percolate through it, the tidal flexing could pump water through the core, generating friction heat. Models suggest this process could produce up to 30 gigawatts of heat, sustaining hydrothermal activity in the ocean above for billions of years. Comparison helps understand the scale of tidal heating. On Earth, tidal forces from the moon and sun generate about 3.7 terawatts of heat, most of it in the oceans through tidal friction. That's about 37 times less than Europa generates. Despite Earth being much larger, Europa, it turns out, is one of the most tidally active bodies in the solar system, exceeded only by Io, which experiences such extreme tidal heating that it's the most volcanically active body we know of. The tidal forces on Europa are about 1,000 times stronger than the moon's effect on Earth. This isn't just because Jupiter is massive, though it is, containing more than twice the mass of all other planets combined, but because Europa orbits so close to Jupiter and experiences such large variations in gravitational force due to its elliptical orbit. This is energy independent of the Sun. It comes from orbital dynamics, from the gravitational dance between moons and planets, from forces that have been operating since the solar system formed and will continue for billions of years to come. Even if the Sun were to suddenly vanish, Europa's ocean would remain liquid for a very long time, sustained by tidal heating alone. It's a reliable, long-term energy source, exactly the kind of energy that life, if it exists in these oceans, could potentially use. And it's not unique to our solar system. Any moon orbiting a giant planet in an elliptical orbit, maintained by resonances with other moons, could experience similar tidal heating. Throughout the galaxy, there might be countless tidally heated ocean worlds, all of them potential cradles for life, all of them independent of their star's warmth. But tidal heating isn't the only potential energy source for life. On Earth, our deepest ocean ecosystems don't rely on sunlight at all. They exist around hydrothermal vents on the seafloor, places where hot, mineral-rich water pours out of cracks in the Earth's crust. The heat comes from the Earth's interior, from radioactive decay and residual heat from the planet's formation. Around these vents, specialized bacteria have evolved to harvest energy not from sunlight but from chemical reactions. They use dissolved chemicals in the vent water, things like hydrogen sulfide and methane, to power their metabolism in a process called chemosynthesis. These bacteria form the base of an entire ecosystem. Tube worms, some growing to lengths of 8 feet, cluster around the vents, their bodies housing billions of chemosynthetic bacteria in specialized organs. Pale crabs and blind shrimp scuttle across the seafloor, feeding on bacterial mats. Fish adapted to high pressure and total darkness hunt among the vent structures. All of this thrives in complete darkness, more than a mile below the ocean's surface, in water that can exceed 400 degrees Celsius near the vent openings. These ecosystems were discovered only in 1977, when scientists in the deep-sea submersible Alvin explored the Galapagos Rift. The discovery revolutionized biology. Before then, scientists assumed all life on Earth ultimately depended on photosynthesis. The sun was thought to be the ultimate source of energy for all living things. But the vent ecosystems proved otherwise. Life could thrive using chemical energy alone, completely independent of sunlight. This discovery transformed astrobiology. If life could exist in Earth's dark oceans, powered by chemistry rather than light, then perhaps life could exist in other dark oceans, like Europa's. Could something similar happen on Europa? The evidence suggests it might. Europa has a rocky mantle beneath its ocean. And if that mantle is in contact with the ocean water, chemical reactions between rock and water could release energy. On Earth, when certain types of rock interact with water, particularly rocks rich in iron and magnesium like olivine and pyroxene, they release hydrogen gas through a process called serpentinization. That hydrogen can then react with other compounds to release energy that organisms can use. The chemistry works like this. When olivine reacts with water, it transforms into serpentine minerals, releasing hydrogen gas in the process. That hydrogen is a powerful reducing agent. If it encounters oxidized compounds, molecules that want electrons, reactions occur that release energy. On Earth, microbes have evolved to catalyze these reactions, harvesting the released energy to build organic molecules and sustain their metabolism. Europa's rocky mantle likely contains similar minerals. If ocean water can penetrate into cracks in the rock, or if the rock is porous enough for water to percolate through, serpentinization could occur. The hydrogen produced could then react with carbon dioxide dissolved in the ocean, potentially forming methane and other organic compounds, releasing energy in the process. Europa's ocean is salty, which we know from the induced magnetic field measurements. Those salts had to come from somewhere, and the most likely source is chemical weathering of the rocky seafloor. Water reacting with rock dissolves minerals, sodium, magnesium, sulfur, iron, carrying them into the ocean. If salts are being dissolved into the ocean, other minerals are too, and those minerals could participate in chemical reactions that release free energy. Scientists have tried to estimate the composition of Europa's seafloor based on what we know about the moon's formation and structure. The leading hypothesis is that the rocky interior is similar in composition to carbonaceous chondrite meteorites, a primitive type of rock that represents the building blocks of the outer solar system. These rocks are rich in water-bearing minerals, carbon compounds, and sulfur. When they react with water, they release a variety of chemicals including hydrogen, methane, hydrogen sulfide, and ammonia. Each of these chemicals represents a potential energy source. On Earth, different microbes have specialized to use different chemical reactions. Some oxidize hydrogen, some use sulfur compounds, some metabolize methane. The diversity of microbial metabolisms on Earth suggests that wherever there are chemical gradients, Differences in chemical concentrations that represent disequilibrium life might find a way to exploit them. There's another possible source of chemical energy on Europa that's unique to its situation. Jupiter's intense radiation bombards Europa's surface, breaking apart water ice molecules and creating oxidants, molecules eager to react with other substances. The radiation splits water into hydrogen and oxygen. The hydrogen, being light, can escape to space, but the oxygen-rich compounds remain, accumulating on the surface over time. These oxidants include hydrogen peroxide, molecular oxygen, and other reactive species. If Europa's surface ice somehow makes it down into the ocean through cracks, subduction, or turnover of the ice shell, those oxidants could mix with reduced compounds from the rocky ocean floor. The meeting of oxidants from above and reduced materials from below would create chemical disequilibrium, a situation where reactions want to proceed to reach equilibrium. And wherever there's disequilibrium, there's free energy that life could potentially harness. Think of it as a battery. The surface, rich in oxidants, represents one electrode. The seafloor, rich in reduced compounds like hydrogen and methane, represents the other electrode. If there's a pathway connecting them, water circulating through the ice shell and down into the ocean, then a chemical circuit completes and energy flows. The water plumes we discussed earlier might play a crucial role in this process. If material is erupting from the ocean to the surface, there could be a return path where surface material eventually makes its way back down. This could create a kind of chemical cycling between the surface and ocean, continuously delivering fresh oxidants to the depths and perhaps returning reduced compounds to the surface where radiation can process them again. Scientists have tried to estimate how much chemical energy might be available in Europa's ocean. The calculations are uncertain, depending on many unknowns, like the exact composition of the seafloor, the rate of water-rock reactions, how much surface material actually reaches the ocean, and how efficiently any hypothetical life could extract the available energy. But even conservative estimates suggest there could be enough energy to support a biomass similar to Earth's deep-sea vent ecosystems. Let's put that in perspective. Earth's vent ecosystems, while locally dense, are sparse when averaged across the entire ocean floor. The total biomass supported by hydrothermal vents is a tiny fraction of the biomass supported by photosynthesis. If Europa's ocean has a similar energy budget to Earth's vents, we might expect a sparse population of microbes, probably clustered near energy sources like hypothetical hydrothermal vents, or perhaps spread thinly throughout the ocean. It wouldn't be a teeming ocean full of fish and whales. More likely, if life exists, it would be microscopic, sparse, eking out an existence from limited energy sources. Microbial mats on the seafloor, perhaps. Maybe biofilms on the underside of the ice shell, if nutrients and energy can reach that far up. But it could exist. The energy budget, as best we can estimate it, seems to allow it. Titan presents an even more complex energy landscape because of its dual ocean nature. In Titan's subsurface water ocean, the energy situation might be similar to Europa's in some ways. Titan has a rocky core, and if that core is porous, allowing water to circulate through it, tidal heating could generate significant warmth. Models suggest this could create conditions for hydrothermal activity, with hot water rising from the core into the ocean, carrying dissolved minerals and heat. However, there's an important difference between Titan and Europa. Titan's ocean is much deeper beneath the surface, separated from space by not just ice, but also by a thick atmosphere. This makes it harder for oxidants from the surface to reach the ocean, reducing one potential source of chemical disequilibrium. On the other hand, Titan's ocean likely contains ammonia, which might enable unique chemical reactions not possible in pure water. Ammonia water chemistry is different from pure water chemistry, and we're only beginning to understand what kinds of reactions might occur and whether they could support life. The bigger question mark on Titan is the surface environment. Here, There's abundant energy from the sun, distant though it is. That energy drives the photochemistry in Titan's atmosphere, breaking apart methane molecules and creating complex organic compounds. Those compounds rain down onto the surface, accumulating over billions of years. The surface also has liquid, in the form of methane and ethane lakes and seas. And occasionally, liquid water might temporarily appear on the surface. When meteorites impact Titan's ice crust, the heat of impact could melt the ice, creating pools of liquid water that might persist for thousands of years before refreezing. Could life exist in this environment? It's one of astrobiology's most intriguing questions. On Earth, all life uses liquid water as a solvent, the medium in which biological molecules dissolve and interact. But could life use liquid methane instead? The chemistry would be completely different. Methane is a non-polar solvent, while water is polar. This affects what kinds of molecules can dissolve and how they interact. The temperature would be much colder, slowing down chemical reactions. But slower doesn't mean impossible. Some scientists have speculated about exotic forms of life that might use liquid methane, perhaps with silicon-based structures instead of carbon-based ones, or with membranes made from compounds that remain flexible at Titan's frigid temperatures. We have no evidence that such life exists. It's pure speculation at this point, but Titan offers the laboratory to test the hypothesis. It has organic compounds in abundance. It has liquid. It has energy, albeit not as much as on Earth. And it's been stable for billions of years, giving time for chemistry to progress. Even if Titan's surface doesn't harbor life, it might preserve a record of prebiotic chemistry. Studying Titan's organic chemistry could teach us about the processes that occurred on early Earth before life emerged. The energy sources on Europa and Titan are fundamentally different from what powers life on Earth's surface. There's no photosynthesis in these dark oceans. Instead, there's the slow, steady warmth of tidal flexing, the chemical energy released when rock meets water, the gradual accumulation of organic complexity in methane lakes under an orange sky. These are not lush, energy-rich environments. They're more like deserts, places where life, if it exists, must be frugal, patient, adapted to scarcity. But Earth has taught us that life can thrive in the most unexpected places, from boiling acidic springs to the driest deserts, to the crushing pressures of the deepest ocean trenches. Life, we've learned, is tenacious. The question is, did it arise elsewhere? And how can we find out? Our understanding of Europa and Titan hasn't come easily. It's the product of decades of robotic exploration, of spacecraft designed and built with exquisite care, launched on journeys lasting years, operated by teams of dedicated scientists and engineers. Let's trace that journey of discovery, celebrating the missions that revealed the ocean worlds. The Galileo spacecraft was not supposed to be a game changer for Europa. When NASA planned the mission in the 1,980 seconds, Jupiter was the main target, with some attention to the Galilean moons as secondary objectives. But exploration often surprises us. Galileo launched in 1989 from the Space Shuttle Atlantis, beginning a 6-year journey to Jupiter. The spacecraft was large and complex, carrying 11 scientific instruments and an atmospheric entry probe. The journey wasn't direct. Galileo swung by Venus once and Earth twice to gain speed through gravity assists, each flyby a delicate dance of orbital mechanics. When Galileo finally reached Jupiter on the 7th of December 1995, the spacecraft fired its engines to enter orbit around the giant planet. Its primary mission was planned for 2 years, with 11 orbits of Jupiter designed to study the planet and make close flybys of the 4 Galilean moons: Io, Europa, Ganymede, and Callisto. But the primary mission was just the beginning. NASA extended the mission multiple times, and Europa became an increasingly important target. By the time Galileo's mission ended in September 2003, the spacecraft had completed 34 orbits of Jupiter and made 11 close flybys of Europa, some passing within a few hundred kilometers of the Moon's surface. It was during these flybys that Galileo's magnetometer made its crucial measurements. The instrument detected the induced magnetic field that would become the cornerstone evidence for Europa's ocean. The data was subtle, requiring careful analysis to tease out the signal from the noise of Jupiter's complex magnetic environment. But the signal was there, consistent and repeatable. Galileo's camera system also returned stunning images of Europa's surface, revealing the cracks, the chaos terrain, the surprisingly few craters. Scientists pored over these images, mapping the surface, measuring the features, trying to understand the processes that had shaped them. The youthful surface suggested active geology, implying that whatever was happening beneath the ice was still happening. The spacecraft also carried a near-infrared mapping spectrometer that analyzed the composition of Europa's surface. It detected water ice, as expected, but also found hints of salts and minerals, particularly in the reddish material that colored some features. This supported the idea that ocean material was reaching the surface. One flyby in particular, the E-12 flyby on the 16th of December 1997, passed just 206 kilometers above Europa's surface. During that pass, Galileo's magnetometer and plasma wave instrument recorded unusual readings: a sudden rotation of the magnetic field and a spike in plasma density lasting about 3 minutes. At the time, scientists couldn't fully explain these anomalies. Only later, when combined with Hubble observations of possible plumes, would researchers realize Galileo had likely flown through an active water vapor plume. Galileo wasn't designed to study plumes. It wasn't designed to detect life. Its instruments were for general planetary science, for understanding Jupiter and its moons in a broad sense. But the data it collected transformed our view of Europa from an icy satellite into a potentially habitable ocean world. The mission had its challenges. Galileo's high-gain antenna failed to deploy properly, forcing the spacecraft to rely on a much slower low-gain antenna for communications. This drastically reduced the amount of data that could be sent back to Earth. Scientists had to be selective, prioritizing which observations to make and which data to transmit. The radiation environment around Jupiter also took its toll, degrading the spacecraft's electronics over time. But Galileo persevered. It continued operating far beyond its planned lifetime, returning data until NASA deliberately crashed it into Jupiter on the 21st of September 2003. To ensure it wouldn't accidentally contaminate Europa with Earth microbes that might have survived on the spacecraft, Galileo's legacy is profound. It provided the first strong evidence for Europa's ocean. It revealed the complexity of Europa's surface. It transformed Europa from a curiosity into a primary target for astrobiology. Everything we're doing now, all the missions being planned to return to Europa, they all build on the foundation Galileo established. If Galileo was a revelation for Europa, Cassini-Huygens was a revolution for Titan. The Cassini-Huygens mission was one of the most ambitious planetary missions ever undertaken. A collaboration between NASA, the European Space Agency, and the Italian Space Agency. Cassini was the orbiter, Huygens, the probe, together weighing more than 5 tons at launch. The spacecraft lifted off from Cape Canaveral on the 15th of October of 1997, beginning a 7-year journey to Saturn. Like Galileo, Cassini took a winding path, using gravity assists from Venus, Earth, and Jupiter to build up the speed needed to reach the outer solar system. It finally entered orbit around Saturn on the 1st of July 2004, beginning what would become a 13-year mission of extraordinary discovery. 6 months after arriving, On the 14th of January, 2005, the Huygens probe separated from Cassini and began its descent through Titan's atmosphere. The probe was designed and built by the European Space Agency specifically for this moment, humanity's first landing in the outer solar system. Huygens plunged into Titan's atmosphere at over 18,000 kilometers per hour. The heat shield protected the probe during the initial descent, and then a series of parachutes deployed, slowing the probe as it descended through the haze. The descent took 2.5 hours, during which Huygens measured atmospheric composition, wind speeds, temperature, and pressure. Its camera snapped hundreds of images of the landscape below. What those images revealed was astounding. River channels carved into the landscape, rounded pebbles scattered across the surface, a network of drainage patterns suggesting liquid had flowed across Titan. The probe eventually landed on what appeared to be a dry lake bed, the surface slightly soft and damp, like wet sand or clay. Huygens operated on Titan's surface for about 90 minutes after landing, transmitting data back to Cassini, which relayed it to Earth. Then its batteries ran out, and Huygens fell silent, its mission complete. But what it had revealed changed everything. Titan had rivers. Titan had weather. Titan had a landscape shaped by erosion and deposition, by cycles of liquid precipitation and evaporation. Cassini continued the exploration. Over the next 13 years, the spacecraft made 127 targeted flybys of Titan, more than any other moon in the Saturn system. Each flyby was carefully designed to observe different aspects of Titan: its atmosphere, its surface, its interaction with Saturn's magnetic field. Cassini's radar instrument could see through the haze that obscured Titan's surface in visible light. Flyby by flyby, the radar built up detailed maps showing mountains, dunes, lakes, seas, river channels, and impact craters. Near the poles, the radar revealed the hydrocarbon lakes and seas, with Kraken Mare stretching over 400,000 square kilometers, larger than the Caspian Sea. The Visual and Infrared Mapping Spectrometer, VIMS, studied the composition of Titan's surface and atmosphere. It detected methane, ethane, and complex organic molecules. It tracked seasonal changes as Titan's northern hemisphere transitioned from winter to summer over the course of Cassini's mission. Scientists watched as clouds appeared and disappeared, as lakes near the North Pole filled with liquid as the seasons turned on an alien world. All the while, Cassini was also gathering the data that would reveal Titan's subsurface ocean. The spacecraft measured Titan's gravity field with exquisite precision, observing how Titan's mass affected Cassini's trajectory during each flyby. These measurements, combined with radar observations of Titan's shape and rotation, built up the evidence for a liquid layer beneath the crust. It was patient work. The evidence accumulated slowly, measurement by measurement, flyby by flyby. But gradually, the picture emerged. Titan has a subsurface ocean of liquid water mixed with ammonia, sitting perhaps 100 kilometers beneath the surface. Cassini also studied other Saturn moons and made the unexpected discovery that Enceladus, another small icy moon, also has a subsurface ocean and is actively venting water vapor and ice particles into space through cracks in its south polar region. This discovery further revolutionized our understanding of ocean worlds. The Cassini mission was planned to end in 2008, but NASA extended it twice, giving scientists more time to study Saturn's complex system. Finally, in September 2017, as the spacecraft was running low on fuel, NASA commanded Cassini to dive into Saturn's atmosphere in a maneuver called the Grand Finale. This ensured that Cassini, which might harbor Earth microbes despite sterilization efforts, would never crash into Titan or Enceladus and potentially contaminate them. On the 15th of September 2017, It was a fitting end for a spacecraft that had transformed our understanding of the Saturn system and revealed Titan as one of the most fascinating worlds in our solar system. The knowledge gained from Galileo and Cassini demanded follow-up. Scientists wanted to return to Europa with better instruments, more flybys, and specific goals of characterizing the ocean and assessing its potential for habitability. Thus was born Europa Clipper. The mission went through many iterations and proposals over the years. Should it be an orbiter, a lander, a flyby spacecraft? Each approach had advantages and drawbacks. An orbiter could study Europa continuously, but would quickly succumb to Jupiter's intense radiation. A lander could directly sample the surface, but would be limited to one location. The solution that emerged was elegant: a spacecraft that would orbit Jupiter, not Europa, and make repeated close flybys of the Moon, diving through Jupiter's radiation belts to collect data and then retreating to safer orbits. Europa Clipper became a flagship mission, NASA's largest spacecraft ever built for planetary exploration. With its solar arrays deployed, the spacecraft spans more than 30 meters, about the length of a basketball court. Those enormous solar arrays are necessary because at Jupiter, more than 5 times farther from the Sun than Earth, sunlight is 25 times weaker. Yet Clipper needs to generate enough power to operate all its instruments during each flyby. The spacecraft launched on the 14th of October 2024 atop a SpaceX Falcon Heavy rocket. The launch was a momentous occasion, the culmination of decades of planning and years of construction. Now, Clipper is on its way, following a trajectory that will take it past Mars for a gravity assist in March 2025, then back past Earth for another gravity boost in December 2026, before finally reaching Jupiter in April 2030. Once at Jupiter, Clipper will spend 3.5 years making approximately 50 close flybys of Europa, with closest approaches ranging from 25 to 2,000. Each flyby will be over a different part of Europa, allowing the spacecraft to build up a nearly global survey of the Moon. Clipper carries 9 science instruments, each designed to answer specific questions about Europa. The Europa imaging system includes both wide-angle and narrow-angle cameras that will photograph Europa at high resolution, studying its geology and looking for signs of active processes like plume eruptions. The radar instrument, called Reason Radar for Europa Assessment and Sounding, ocean to near surface, will send radio waves through Europa's ice shell to measure its thickness and look for lakes or liquid water within the ice. This is crucial data. Knowing how thick the ice is will tell us how accessible the ocean might be and whether there are any shortcuts to reaching it. The magnetometer and a complementary instrument called PIMS plasma instrument for magnetic sounding will work together to confirm the ocean's existence and measure its depth and salinity. They'll study how Europa's induced magnetic field changes during each flyby, refining our understanding of what lies beneath. The thermal imager, E-Themis, will map Europa's surface temperature, looking for warm spots that might indicate recent eruptions of water or areas where the ice is thinner and heat from below can reach the surface more easily. The ultraviolet spectrograph will study Europa's thin atmosphere and look for plumes erupting from the surface. 2 instruments are designed to sample any material ejected from Europa. SUDA Surface Dust Analyzer will collect and analyze tiny ice grains, while MASSPEX, Mass Spectrometer for Planetary Exploration, will analyze gases. If Europa is actively venting material from its ocean, these instruments could directly sample it and determine its composition, looking for salts, organics, or other compounds that would tell us about the ocean's chemistry. Finally, Clipper will use its communication system as a science instrument. By precisely measuring small changes in the spacecraft's radio signals caused by Europa's gravity, scientists can map Europa's gravitational field and learn about how mass is distributed inside the Moon. These measurements will reveal how Europa flexes in response to Jupiter's tides. All of this data, collected over dozens of flybys, will paint the most detailed picture yet of Europa. Is the ocean really there? How deep is it? How salty? How thick is the ice? Are there plumes? Is there active geology? What's the surface composition? Could the ocean support life? Clipper won't land. It won't drill through the ice. It won't directly detect life, but it will answer the questions we need to answer before we can consider sending a lander or a submarine to Europa. It will, in essence, scout the territory, identifying the best places to explore further and determining whether Europa truly deserves the immense effort and cost of a lander mission. The mission is scheduled to end around 2034, though it could be extended if the spacecraft remains healthy. To protect Europa from contamination, Clipper will be deliberately crashed into Ganymede or Callisto at the end of its mission, ensuring it never accidentally impacts Europa. While Clipper will be exploring Europa, another revolutionary mission will be making its way to Titan. Dragonfly represents a completely new approach to planetary exploration. A flying robot that will explore multiple sites across an alien world. Dragonfly is a rotorcraft, essentially a large drone with 8 rotors arranged in a quadcopter configuration for redundancy. Each rotor is 1.35 meters in diameter. The entire vehicle is about the size of a small car, and it will fly on Titan. This sounds audacious, perhaps even reckless, until you consider Titan's environment. The atmosphere is thick, providing plenty of lift. The gravity is low, just 1/7 of Earth's. These conditions make flying on Titan easier than flying on Earth, despite the extreme cold and the fact that Titan is 1.4 billion kilometers away. Dragonfly is scheduled to launch in July 2028 on a SpaceX Falcon Heavy rocket. It will take 6 years to reach Titan, arriving in 2034. The same year Europa Clipper will be conducting its science campaign at Jupiter. The 2030 seconds promise to be an extraordinary decade for ocean world exploration. When Dragonfly reaches Titan, it will plunge through the atmosphere protected by a heat shield, deploying parachutes to slow its descent. The landing site will be in the Shangri-La Dune Fields, not far from Selk Crater, an 80-kilometer impact structure that's of particular scientific interest. Once on the surface, Dragonfly will begin a mission unlike any before it. Rather than being stuck in one place like a traditional lander, Dragonfly will fly. It will take off, travel several kilometers or even tens of kilometers, and land at a new site to conduct measurements. Then it will fly again, gradually traversing across Titan's landscape. Each flight will be carefully planned. The rotorcraft is designed to operate autonomously, making real-time decisions about navigation and safety without waiting for instructions from Earth, which would take over an hour to arrive. Dragonfly will fly during Titan's day, which lasts about 16 Earth days, allowing its cameras and sensors to see the landscape. It will recharge its batteries from a radioisotope thermoelectric generator, RTG, during Titan's nights, which last equally long. Over its planned 3.3-year mission, Dragonfly will visit more than 24 sites, covering up to 115 kilometers total distance. This mobility will allow it to study diverse environments, organic sand dunes, interdune regions, the icy rim of Selk Crater, and possibly areas where liquid water might have temporarily existed after the crater-forming impact. Dragonfly carries 4 main scientific instruments. The DRAMS, Dragonfly Mass Spectrometer, will analyze samples of Titan's surface and atmosphere, looking for organic molecules and determining their composition. This is crucial for understanding how far prebiotic chemistry has progressed on Titan. The DRAGMET, Dragonfly, Geophysics and Meteorology package includes sensors for measuring weather conditions, seismic activity, if any, and electromagnetic properties of the surface. The DRAGNS, Dragonfly, Gamma Ray, and Neutron Spectrometer will determine the elemental composition of the surface from afar. mapping the distribution of different materials. And cameras, of course. Dragonfly will carry cameras to navigate, to study the terrain, to document its journey across this alien world. The images will be spectacular. A drone's eye view of Titan's dunes and mountains and river channels, all under an orange haze. One of Dragonfly's key science goals is to search for chemical biosignatures, evidence of biological processes, either past or present. This doesn't mean Dragonfly will definitely find life, but it will look for the kinds of molecular patterns that, on Earth, are associated with biology. Certain amino acids in specific chiralities, particular molecular mass distributions, unusual concentrations of elements that might suggest metabolic processes. Dragonfly will also study Titan's methane cycle, trying to understand where the methane comes from. Methane in Titan's atmosphere should be destroyed by sunlight in about 30 million years, yet Titan has abundant methane. Something must be replenishing it, but we don't know what. Volcanic activity bringing methane from the interior? Methane locked in icy clathrates being released? Understanding the methane cycle will teach us about Titan's interior and its long-term evolution. The mission explicitly incorporates the search for signs of life into its goals, making Dragonfly, along with the Mars rover Perseverance, the first NASA mission since the Viking landers in 1976, to explicitly look for biosignatures. Dragonfly recently passed its critical design review, a major milestone confirming that the design is mature and construction can proceed. Teams are now building and testing the hardware that will fly to Titan. It's remarkable to think that within a decade, a robot will be flying across Titan's surface, sampling its organic-rich landscape, searching for clues to how life might begin. These missions, Galileo and Cassini in the past, Clipper and Dragonfly underway and upcoming, represent humanity's expanding reach into the outer solar system. Each builds on what came before. Each asks questions that couldn't be asked until the previous mission provided answers. Together, they're writing the story of ocean worlds, a story that's still unfolding. We've traveled through the evidence, traced the missions, understood the energy sources. Now, as our journey through the ocean worlds draws toward its close, let's step back and contemplate what all of this means. Not just scientifically, but philosophically. What does it mean for our understanding of life, of habitability, of our place in the universe? For most of the history of astrobiology, the search for life beyond Earth focused on the habitable zone, sometimes called the Goldilocks zone, the region around a star where a planet receives just the right amount of heat to maintain liquid water on its surface. Not too hot, not too cold. This made sense. On Earth, life needs liquid water, and Earth's water remains liquid because we orbit at the right distance from the Sun. Apply this logic to other star systems, and you can identify planets that might have similar conditions. This approach has guided the search for exoplanets and shaped which worlds we consider most likely to harbor life. But Europa and Titan have forced us to reconsider. These moons orbit far beyond the traditional habitable zone of our solar system. If the habitable zone is defined by where sunlight can keep water liquid, then Jupiter and Saturn are well outside it. Their moons receive only a small fraction of the sunlight that Earth does. By the traditional definition, they should be frozen, lifeless ice balls. Yet here we are, with strong evidence that Europa has a global ocean of liquid water, that Titan has a subsurface water ocean and surface hydrocarbon lakes, that these oceans have existed for billions of years. The heat keeping them liquid doesn't come primarily from the sun. It comes from within, from tidal forces, from orbital dynamics, from the gravitational relationships between moons and planets. This realization has profound implications. It means habitability isn't just about distance from a star. Internal heat sources matter. Tidal heating matters. The composition of a world matters. A moon orbiting a giant planet far from the sun might be more habitable than a planet orbiting alone at the right distance from its star. The implications are staggering when we think about planetary systems beyond our own. Consider a planetary system with a giant planet like Jupiter or Saturn orbiting in the cold outer reaches, well beyond the habitable zone. Traditional thinking would dismiss this system as unlikely to harbor life. The giant planet is too far from its star, too cold, gas rather than rock. But if that giant planet has a moon in an elliptical orbit, maintained by resonances with other moons, that moon could have a tidally heated ocean. It could be habitable, despite being far from its star. Now consider how common such situations might be. We've discovered thousands of exoplanets since the first confirmed detection in 1995, and many of these are giant planets, some even larger than Jupiter. While we can't yet detect moons around exoplanets, they're too small and too faint for our current instruments. There's no reason to think giant planets elsewhere wouldn't have moons like our solar system's giant. Planets do. If Jupiter has 95 known moons and Saturn has over 140, why wouldn't exoplanets have similar retinues? And if those exomoons can have the right characteristics, elliptical orbits maintained by resonances, icy compositions with internal oceans, rocky cores where water can react with rock, then they could be habitable. The number of potentially habitable environments in the galaxy might be vastly larger than we thought. Let's do some rough math. Our galaxy contains perhaps 100 to 400 billion stars, depending on how you count. Conservative estimates suggest that most stars have at least one planet. Observations from the Kepler Space Telescope suggest that giant planets are common, perhaps orbiting 10 to 20% of stars. If even a small fraction of those giants have moon systems, and if even a small fraction of those moons are ocean worlds like Europa, we could be talking about millions or even billions of ocean worlds in our galaxy alone. This doesn't even account for ocean worlds that might exist as rogue planets. Some theoretical models suggest that worlds ejected from their star systems to wander through interstellar space could maintain subsurface oceans for billions of years, if they have thick enough ice shells to insulate their interiors and enough radioactive isotopes to provide heat. These worlds would be invisible to our current detection methods, dark and cold, but potentially habitable beneath their frozen surfaces. Recent estimates suggest there might be more rogue planets than stars in the galaxy. The ocean world's paradigm shift also changes how we think about the timeline of habitability. A planet in the traditional habitable zone might have liquid water for only part of its history. As its star evolves, brightening over billions of years, the habitable zone moves outward. A planet that's habitable now might become too hot as its star ages and its luminosity increases. Conversely, a planet that's too cold now might warm up and become habitable later, but the window of habitability is limited by stellar evolution. Ocean worlds with internal heat sources could remain habitable for much longer, as long as their tidal heating or radioactive decay continues. Tidal heating can persist for billions of years if the orbital resonances remain stable. Radioactive decay provides heat for billions of years as heavy elements slowly transform. These heat sources don't depend on the star's evolution. An ocean world could be habitable for the entire lifetime of its planetary system, potentially 10 billion years or more. And if this is true in our solar system, it's likely true elsewhere. Throughout the galaxy, there are countless giant planets, many of them probably hosting systems of moons. If those moons have the right characteristics, elliptical orbits maintained by resonances, icy compositions with internal oceans, they could be habitable. The number of potentially habitable environments in the galaxy might be vastly larger than we thought. In our solar system alone, we now know of several ocean worlds. Europa, certainly. Enceladus, Saturn's small but geologically active moon, definitely has a subsurface ocean and active water plumes jetting material into space. Titan likely has one beneath its organic rich surface. Ganymede and Callisto, two other Galilean moons, show evidence that they might have subsurface oceans too, though we know less about them than we do about Europa. Some scientists even suspect that Mimas, another moon of Saturn, might have a hidden ocean beneath its heavily cratered surface. That's potentially 5 or 6 ocean worlds in our solar system, and there may be more waiting to be discovered. 5 or 6 ocean worlds. 5 or 6 potentially habitable environments. Not on the surfaces of planets in the habitable zone, but hidden beneath ice, in darkness, heated by forces we're only beginning to fully understand. Each one a possible experiment in the origin of life, a possible answer to the question of whether we're alone. This doesn't mean we should stop looking for Earth-like planets in the habitable zones of other stars. Those worlds are still important, still compelling targets. They might be more likely to have complex life that could develop technology and civilization, life we could communicate with. They're easier to study remotely. We can analyze their atmospheres, look for biosignatures like oxygen and methane, search for technosignatures like industrial pollutants or artificial light. Surface oceans could support photosynthetic ecosystems, producing much more biomass than chemosynthetic systems in dark oceans. But it means we need to expand our concept of what habitability means. It means life might be hiding in places we wouldn't have thought to look. It means the universe might be more alive with possibility than we imagined. If life exists in Europa's ocean, it has never seen sunlight. From the moment the first hypothetical microbe came into being to the present day, every generation would have lived in complete darkness, knowing only the cold pressure of the deep ocean, the warmth of hydrothermal vents if they exist, the taste of minerals dissolved from rock. This isn't unprecedented on Earth. In the deep ocean, below the reach of sunlight, entire ecosystems thrive. Around hydrothermal vents, where superheated water rich in minerals pours out of cracks in the seafloor, communities of tube worms, crabs, fish, and other creatures make their living. None of them rely directly on sunlight. None of them photosynthesize. At the base of these ecosystems are bacteria that harvest energy from chemical reactions. They oxidize hydrogen sulfide or methane or other reduced compounds in the vent water, using the released energy to build organic molecules from carbon dioxide. These bacteria are primary producers, but instead of photosynthesis, they perform chemosynthesis. Other organisms eat the bacteria. Still others eat the organisms that eat the bacteria. A food web emerges, complex and interconnected, all based on chemical energy from Earth's interior rather than light from the sun. Could similar processes occur on Europa? The ingredients seem to be there. A rocky seafloor where water-rock reactions could release hydrogen and other reduced compounds. Potentially hydrothermal vents if tidal heating creates enough warmth, an ocean with dissolved minerals and salts. If Earth's vent ecosystems are any guide, these conditions might be sufficient for life. The life, if it exists, would likely be simple, microbial, single-celled organisms, perhaps forming mats or films on rocks, perhaps floating freely in the water. Don't expect fish or whales or anything complex. But microbes might thrive, or at least persist, adapted to the scarcity, making do with what's available. On Titan, the question becomes even more exotic. Could life exist in liquid methane? All life on Earth uses water as a solvent, the medium in which biochemical reactions occur. Water has unique properties that make it excellent for this role. It has a high heat capacity, buffering against temperature changes. Methane is different. It's non-polar, so it dissolves different kinds of molecules than water does. It's liquid only at very low temperatures, around Titan's surface temperature of -179 Celsius. Chemical reactions in liquid methane would proceed much more slowly than in water. But slower doesn't mean impossible. Some scientists have speculated about hypothetical life forms that might use liquid methane or ethane as a solvent. Such organisms would need to be chemically very different from Earth life. Their membranes might be made from compounds like acrylonitrile instead of phospholipids. Their metabolism might involve different chemical reactions. They might even use different elements in key roles. There's no evidence such life exists. It's speculation, thought experiment, an exploration of what might be possible at the edges of our understanding. But Titan offers the opportunity to test the hypothesis. If we find life there, or even complex organic chemistry that seems to be heading in the direction of life, it would teach us that life's possibilities are broader than we imagined. Even if we don't find life, studying Titan's chemistry will teach us about prebiotic processes, the steps that lead toward life but don't quite cross the threshold. Titan might be like a frozen snapshot of the early Earth before life began, preserving in its cold environment the kinds of chemistry that occurred in our planet's youth. How do we search for life in a subsurface ocean? We can't see it with telescopes. We can't easily drill through kilometers of ice. The challenge is daunting, but not insurmountable. The water plumes on Europa, if they're real and recurring, offer a shortcut. Material from the ocean, ejected into space, could be sampled by a spacecraft flying through the plume. This is exactly what Europa Clipper might do, using its dust and gas analyzers to study the composition of plume material. If the plume carries organic molecules, salts with particular isotopic signatures, or even cell fragments, we might detect them. But detecting biosignatures from a distance is tricky. We need to know what to look for, and we need to distinguish biological processes from abiotic chemistry that might produce similar molecules. On Earth, certain patterns are strongly associated with biology. Amino acids come in left-handed and right-handed versions, but Earth life uses almost exclusively left-handed amino acids. Finding that preference on Europa might suggest biology. Similarly, certain molecular mass distributions or unusual concentrations of particular elements might hint at metabolic processes. But these clues are subtle. We'd need to be very careful about jumping to conclusions. The history of astrobiology is littered with false alarms, from the supposed Martian meteorite fossils to the debunked arsenic-based life. Titan presents different challenges. The prebiotic chemistry on Titan's surface is rich and complex, but how do we distinguish between chemistry that's just proceeding through natural processes and chemistry that's crossed the threshold into biology? Dragonfly will look for patterns, for molecular signatures that don't fit purely abiotic explanations. But this is detective work of the most painstaking kind. The ultimate answer might require landing on these worlds. A Europa lander that could drill even a few meters through the ice, or melt its way deeper, could sample subsurface materials directly. A Titan submarine that could dive into Kraken Mare and sample the lakebed could look for signs of exotic life adapted to liquid hydrocarbons. These missions are far in the future, decades away at least. They'll be expensive, complex, fraught with technical challenges, but they're not impossible. Engineers are already sketching concepts, running simulations, testing technologies. Someday, perhaps in the lifetime of people alive today, we might deploy a robot submarine into an alien ocean. And if we find life, if we discover that Europa's ocean or Titan's methane seas harbor living organisms, even simple ones, the implications would be staggering. It would mean life arose at least twice in our solar system, independently. And if it arose twice here, in our one solar system among billions, then life is probably common in the universe. There might be billions of ocean worlds in the galaxy, billions of potential cradles for biology. We might live in a universe teeming with life, even if most of it is microbial, hidden away in dark oceans beneath frozen shells. Alternatively, If we explore these worlds thoroughly and find no life, that tells us something too. It tells us that having liquid water and chemical energy isn't enough. There must be other requirements we don't yet understand. It tells us that life might be rarer, more precious, perhaps even unique to Earth. That knowledge, while perhaps disappointing, would still be profound. Either way, we learn. Either way, our understanding deepens. There's a certain irony in how the search for life has evolved. For decades, Mars was the focus. The red planet, our neighbor, tantalizing in its similarities to Earth. We sent rovers and landers, studied its geology, searched for ancient water, looked for organic molecules. Mars is still important, still a primary target in astrobiology, but increasingly, the scientific community's attention has turned to moons, not the large rocky planets orbiting in the habitable zones of distant stars, not the desert world next door that once had rivers and lakes but lost them billions of years ago. Moons, small, icy satellites of giant planets in the cold outer reaches of the solar system. Places we barely knew existed until a few decades ago. This shift reflects our growing understanding that life doesn't require the conditions we once thought essential. It doesn't need sunlight if it has chemical energy. It doesn't need a rocky surface if it can float in an ocean. It doesn't even necessarily need moderate temperatures, though the cold of the outer solar system presents challenges. What life needs, as far as we can tell, is liquid, energy, and the right chemical ingredients. Europa and Titan have all three. That makes them prime targets, perhaps even better targets than Mars, for finding extant life, life that's alive right now. And yet, we're still learning about our own solar system, still discovering secrets about worlds that have been visible to humans for millennia. Jupiter's moons were discovered in 1610, but we didn't know they had oceans until the 1990 seconds. Saturn's moons have been observed for centuries, but we didn't understand Titan's surface until 2005. Each mission rewrites textbooks. Each discovery generates new questions. When Voyager revealed Europa's smooth surface, scientists asked, "What could cause that?" Galileo answered, "Probably a subsurface ocean." Then scientists asked, "How thick is the ice? How deep is the ocean? What's in it?" Those are the questions Europa Clipper will address. And Clipper's answers will generate new questions that the next mission will attempt to answer. This is the nature of science. A slow, methodical accumulation of knowledge, each answer revealing new layers of mystery. It can feel frustrating if you want immediate answers, but there's beauty in the process, in the patience required. The ocean world's story is still being written. We're in the middle chapters, past the initial discovery, approaching the deeper investigation. The climax, if there is one, might come decades from now, when a lander or submarine samples an alien ocean directly and returns data that confirms or rules out the presence of life. But even now, in this in-between time, there's wonder in the waiting. There's beauty in not knowing yet, in holding the question while the missions fly and the instruments gather data and the scientists analyze and debate. The universe has revealed that it contains hidden oceans on icy moons. What else might it be hiding? What other surprises await? We stand on a threshold of understanding, looking toward oceans we cannot see, imagining life we may never encounter, dreaming of submarines diving into alien seas. And in this moment of anticipation, of possibility, we can reflect on how strange and marvelous our solar system has proven to be. Not barren, not dead, but dynamic, complex, full of places where water flows in darkness, where energy pulses through rock and ice, where chemistry progresses in ways we're only beginning to understand. Life might thrive in those dark oceans, or it might not. But the possibility has expanded our vision, broadened our definitions, and reminded us that the universe is more creative, more surprising than we can easily imagine. These oceans exist. That much we know. What they contain, what secrets they hold, what stories they could tell, those questions remain open. The answers await us, patient as the oceans themselves, ready to be discovered when we're ready to seek them. We've traveled far tonight, from Jupiter's radiation-scoured moon with its fractured ice shell to Saturn's hazy giant with its methane lakes and hidden water ocean. We've traced the evidence that revealed these oceans: magnetic field measurements, surface features, tidal bulges, plumes of water vapor erupting into space. We've explored the energy sources that keep these oceans liquid despite the cold and darkness. Tidal heating from gravitational dances, chemical reactions where water meets rock, the slow circulation of fluids through porous cores. We've celebrated the spacecraft that discovered these secrets. Galileo, flying through Jupiter's radiation to measure Europa's induced magnetic field. Cassini, making 127 flybys of Titan to map its surface and detect its subsurface ocean. Huygens, descending through orange haze to land on an alien shore. And we've looked ahead to the missions to come. Europa Clipper, preparing to make 49 close passes of the ocean moon starting in 2030. Dragonfly, readying to fly across Titan's landscape beginning in 2034. Europa and Titan are different in almost every way. Europa is small, smooth, young, geologically active, its ocean perhaps just 15 to 25 kilometers beneath the surface. Titan is large, hazy, organically rich, with a thick atmosphere and two oceans, one of methane on the surface, one of water ammonia mixed 55 to 80 kilometers down. Europa likely has energy from tidal heating and water rock chemistry, creating conditions similar to Earth's deep-sea vents. Titan has both a subsurface ocean that might host life as we know it, and a surface environment where exotic chemistry occurs in liquid hydrocarbons, potentially hosting life as we don't know it. Yet, for all their differences, both moons represent the same fundamental shift in our understanding. They've taught us that habitability isn't just about being in the right place around a star. It's about having the right conditions: liquid, energy, chemistry. Those conditions can exist in darkness. They can exist far from the sun. They can persist for billions of years, giving time for chemistry to progress, for complexity to emerge, perhaps even for life to take hold. The evidence has accumulated over decades, from speculation in the 1,970 seconds to confirmed oceans in the 2000s to detailed characterization in the decades ahead. Each generation of spacecraft has been more capable, more sophisticated. Each has answered questions the previous generation raised and posed new questions for future missions to address. Standing where we are now, in the middle of this unfolding story, we know enough to be confident that these oceans exist, but not yet enough to know what they contain. We have strong hypotheses, but no definitive answers. We have hope, but not yet confirmation. This is perhaps the most exciting place to be. Not at the beginning, when everything was unknown. Not at the end, when all questions are answered. But here, in the middle, where we know enough to ask meaningful questions and have the technology to seek answers. The 2030 seconds will be a remarkable decade. Europa Clipper will be flying past the ice moon, measuring its ocean's depth and salinity, searching for plumes, mapping the surface in exquisite detail. Dragonfly will be hopping across Titan's surface, sampling organic-rich dunes and crater materials, looking for biosignatures. Both missions operating simultaneously, exploring ocean worlds at opposite ends of the outer solar system. And what will they find? Will Europa's plumes yield organic molecules, suggesting life in the ocean below? Will Dragonfly detect chemical patterns that can only be explained by biology? Will we finally answer the question that has haunted humanity since we first looked up at the stars? Are we alone? Or will the answers be more subtle, more ambiguous? Will we find intriguing hints that demand follow-up missions? Will we discover that these worlds, while fascinating, show no clear signs of life? Will the question remain open, driving us to send submarines and drills and landers in search of more definitive evidence? We don't know yet, and there's a strange beauty in that uncertainty, in the patient waiting while the missions fly and the data accumulates and the analyses proceed. Science is slow. Understanding builds gradually, but the waiting is filled with wonder. Somewhere out there, right now, as you hear these words, Europa orbits Jupiter, its ocean sloshing beneath the ice, perhaps hosting microbes that have never known light. Titan circles Saturn, methane rain falling from its orange sky onto organic-rich sand, while deep below, a water ocean sits in darkness, keeping its secrets. These worlds exist. These oceans are real. And in seeking to understand them, in sending our robots across hundreds of millions of kilometers to measure and sample and photograph, we're expanding not just our knowledge, but our sense of what's possible. Life might exist in darkness. Oceans might thrive without sunlight. Habitability might be more common, more varied, more resilient than we imagined. The universe might be more alive, more dynamic, more full of possibility than we dared to hope. Or we might find that even with all the right ingredients, life is rare, arising only under conditions we don't yet understand. That would teach us something too, about the value of the life we know, about how precious our own world is, about how careful we should be with the only place we know for certain harbors living things. Either way, the search continues. The missions fly, the questions evolve, and we, standing on our own ocean world, looking out at moons with hidden seas, can marvel at the strangeness and wonder of it all. Before we part ways tonight, if this journey has resonated with you, if these hidden oceans have sparked your curiosity or wonder, I'd be grateful if you'd take a moment to leave a like on this video. It helps others find these explorations. And if you'd like to continue traveling to distant worlds together, to explore more mysteries of the universe, consider subscribing. There are so many more stories to tell, so many more secrets waiting to be uncovered. Thank you for joining me on this voyage to the ocean worlds, for letting me guide you through the evidence and the missions, the science and the speculation, for wondering with me about life in the darkness, about hidden seas on frozen moons, about the expanding boundaries of what we call habitable. As you drift off tonight, perhaps you'll dream of Europa's fractured ice, of Titan's methane seas, of oceans no human eye has ever seen. Perhaps you'll imagine what might swim in those dark waters, what chemistry might be unfolding in hydrocarbon lakes, what secrets await discovery. Rest well, wonder gently, and remember, some of the most profound possibilities in the universe might be hiding not under distant stars, but right here in our cosmic neighborhood, beneath the ice, in the dark, in oceans we're only beginning to understand. Good night.